So, this video we will see about we will discuss about the Bragg-Williams approximation. Bragg-Williams is otherwise called the Zeroth approximation of the Ising model. Okay, so it goes by both the names. Basically, to tell you more about that, we have already discussed about the Ising model in the previous class. So basically, the Ernst Ising was trying to explain the spontaneous magnetization observed in ferromagnets. More than that, its significance can be understood that it is an attempt to unravel the statistical mechanics of phase transitions. So as I told you in that class itself, the critical part in that process was to come up with a model which can explain the phase transitions which were observed in the critical temperature which was observed in the case of ferromagnets. Here, this Bragg-Williams approximation is basically an attempt to solve the Ising model. In that class, we have derived a partition function of the Ising model, right? So, the Bragg-Williams approximation is basically an attempt to solve the Ising model and to show that there can be a critical temperature. Okay. So here the assumption is that the energy involved in transferring an atom from an ordered to a disordered state is directly proportional to the average degree of order prevailing in the entire system. Let me write it down for you. Here, the assumption is that the energy involved in transferring an atom from an ordered state to disordered state is proportional to the average degree of order prevailing in the system. So it should be understood like this. So basically you will know that the Ising model is trying to explain the magnetism, right? So here the order means if two spins or more spins are arranged in the same direction, this amounts to an ordered state, right? This represents an ordered state. Whereas disordered state is what you see in the case of a, say, a case of a paramagnet. I have something like this, I have something like this, like this. So this is a disordered state. So if I want to make an ordered atom like this, so for example, this spin. If I want to make this ordered atom to a disordered state like this, I need to spend some kind of energy, right? Because this is well ordered, I need to break this order. That means I have to supply some kind of energy in order to break this system. So this breaking, the energy required for breaking, is not dependent on only on the immediate neighbors, but it is dependent on the overall degree of order prevailing in the system. For example, this atom is having an immediate neighbor which is having the same direction of spins as the atom which we are considering. But it is not only dependent on this one, but it is totally dependent on the average degree of order prevailing in the whole system, say of n atoms. And that order should be considered while we discuss about the dynamics of the spin quantum number of this system. That is what the zeroth approximation of the Ising model or the Bragg-Williams approximation is trying to explore. So in a way, this model is totally what we can tell that the totally discard the fluctuating the fluctuating local order, right? So if we are concerned about a local order, it will be more kind of fluctuating. Whereas if we consider the average effect of the whole lattice of say n atoms or the n lattice points, that will be more stable because it's having a statistical information built into it. So therefore, this model is equivalent to it is generally told to be equivalent to the mean, the mean molecular field theory, or it's a part of the mean molecular field theory. And another thing, or another point which we should consider is that why this is called the zeroth approximation. It is called zeroth approximation because it is totally insensitive to the detailed structure of the, or say, dimensionality of the lattice, right? Because it is only concerned about the overall or the average number. So it is totally insensitive to the detailed structure or the dimensionality of the lattice. This model, so the question is that how to make this model more accurate. So whenever we are trying to work on this model, one of the major assumptions which we should build into the system is that the more the number of interacting neighbors for a given atom, the more reliable the model will be. so that the effect of this local field can be neglected, right? So if you remember that diagram, say I have one lattice point like this, and I can have different neighbors like this. So these are the nearest neighbor of this two-dimensional lattice, this for this red one, whereas these are the next nearest neighbors for this one. For say this atom, for this lattice point, these are its nearest neighbors. As the number of nearest neighbors increases, the effect of the local fluctuating magnetic field. For example, this atom is vibrating because of some effect, right? So it will affect the kind of magnetic interaction between these two lattice points. But if we take the overall lattice of say a large number of atoms, say n atoms, this effect, this individual fluctuating effect, the effect of the fluctuating effect can be reduced. Extending that, if I have now here the 4 kind of nearest neighbors, imagine a situation where I can have say 8 nearest neighbor kind of lattice. There are crystal structures which offer that kind of flexibility or the luxury. So that will make the contribution of one of the vibrations negligible compared to the other ones. Okay. So we will continue in the next video with some more or more kind of discussion into the zeroth approximation.